to present this session to such an audience, and well, I hope you enjoy it. And well, I did my PhD here, as Daniel said, and it was about time series forecasting models, so it's related to the current session. And in fact, some of the things that I'm going to present correspond to part of the work I did during the PhD. Okay, let me first start giving presenting the schedule for the session. This session corresponds to chapter 29 of the Probabilistic Machine Learning book, and I will start giving a brief introduction about the state space models. Then I will continue with a review of some key model families, putting special emphasis on what in the book are called structural time series models, for which I will present two real-world use case examples. And then I will end up with some conclusions. Okay, first, what is a state space model? State space models are a type of partially observed Markov models in which hidden states set sub t evolve according to a Markovian process. So at time t plus one, the state only depends on the previous one, and they generate some observations yt at each of the time steps. And depending on the applications, when using this type of models, we are usually interested in one of two main objectives. One is to infer the hidden states. For example, this has been used in predictive maintenance of machine parts, in which the hidden states could be identified as new part, a slightly worn part, or heavily worn part. And it has also been used, for example, in identifying brain activity states from electroencephalogram data. And the other main objective when using this type of models is to predict future observations. For example, when doing weather forecasting or sales forecasting from historical demand data and other possible inputs. Okay, and any state space model is defined in its most general form by two parts. One is what is called the transition model for the states, and other the observation model for the observations. And in a probabilistic manner, they can be expressed as we can see here. We have for the states, the probability of the states depends on a function which can be linear or not, depending on the previous state and some possible inputs u sub t. And for the observation, we similarly have another function which also can be linear or not. That depends on the current state, some possible inputs, and all the previous observations. And a slightly more simple version of this is represented here in this on the right on this graphical model. This is a bit more simple because in this case the current observations only depends on the last one, not all the previous ones. And the blue dots represent the variables we observe, that is the inputs on the observations, and the hidden states are hidden and we cannot observe them. Okay, and let's see now some of the key model families. One of them is hidden Markov models, which are a type of state space models in which the hidden states sub t are discrete. For example, they take values from 1 to some capital K. And the observations can be discrete or continuous. The hidden states are Markovian. And usually in the standard hidden Markov model, the observations are independent and identically distributed, conditioning on the current states. That's why we here do not have an arrow between the current observation and the previous one. And well, like any state space model, it is defined by two parts, the state transition model and the observation model. Well, the state transition model is defined by initial state distribution for the first state set sub 1 and a raw stochastic matrix that defines the probability of transitioning for one state y to another one g. Uh, Here we can see a really simple example with just three states. And as I said, the matrix A is a row stochastic matrix, and the row corresponding to the to state Y, if we sum of the elements, is the probability of going from it to all other states. So if we sum those elements, it will add up to one. Okay, and the other part of any state space model is the observation model, which for hidden Markov models, as we saw on the previous slide, these observations can be discrete, for example, a categorical distribution or a Poisson, or continuous, for example, a normal distribution. And we could even consider and are introduced in the chapter 29 of the book some variants like an autoregressive hidden Markov model in which the condition that the observations are independent and identically distributed conditioned on the states is not fulfilled, but instead the current observation depends on some capital L last observations. And we could also even consider some neural network likelihood for the observation model. And for parameter learning, there are several options. The traditional one is to use an expectation maximization algorithm called Baum-Welch algorithm, which is an iterative optimization bound algorithm, which it's assured to converge to at least a local optima. A problem with this type of algorithm is that it doesn't scale all that well to large data sets. So in those cases, an alternative is to use a stochastic gradient descent, which scales better to large data sets. Another option is to use spectral methods, either standalone or even as initial parameters for the expectation maximization algorithm. And we could also even use some Bayesian approach like blocked Gibbs. Okay, so the traditional Braun-Welch algorithm, as I said, is an iterative optimization process. And at each iteration, the likelihood improves, and the stop criteria is when the improvement in the likelihood is not significant. And in this algorithm, we start first by initializing the parameters theta, which the parameters theta are the state transition matrix A. The capital B will be the parameters of the observation model, and P the distribution for the initial state set sub 1. And the A step of this algorithm is consist on first initializing. Well, first we initialize the parameters theta either randomly or using some prior information, and then we start the iterative processes, which has the E step, which starts initializing the expected counts, and then for each data case, using forwards-backwards algorithm to compute what we had defined here as gamma and chi, which is the probability of being in a given state and the probability of transitioning from one to another, given the current parameters. Once we have this, we can compute the new expected counts and use this in the M step to compute the new parameters with the equation that we have here for each of the parameters of the model. Okay, and another key model family that we have is what is called in the book a linear dynamic system or linear Gaussian state space model. which is defined with two parts, the observation model here and the transition model between of the states. And if we incorporate the inputs user t into the block structure matrices F and G and also the state set, we get what is the common notation for what is also called a dynamic linear model or DLM, which has which looks like this in the standard representation. But I'm going from this point onwards on this session use this other notation in which we substitute set that notation for the states with theta sub t, which again will include in case there are any inputs, they will be included in this state. And here we have what really is the most common notation for this type of structural time series models. This model is defined by two matrices, the observation matrix and the state evolution matrix G. And initial distribution, well, actually the mean and variance of the initial of the distribution for the initial parameter theta sub 0. The dimensions of matrix of the observation matrix depend of whether we have a univariate model, in which case this will be just an scalar and m will be 1, and the dimensions will be 1 by m by p, and the state evolution matrix have corresponding dimensions p by p. And these type of models are really flexible because they allow to have different model components to take into account different effects commonly present in time series, like trends, seasonalities, covariates that are useful for forecasting, etc. And the incorporation of these different types of building blocks or model components results in in a diagonal block matrix. And for example, for if we have three model components, the state evolution matrix G will look like this with a submatrix for the first component 8, another submatrix in the diagonal for the other component B, and another submatrix for the last component of the model or building block C. And these building blocks can be just standalone or combined into a bigger model with different building blocks for different effects. One of the most common one, and that is present in almost all practical applications of the DLMs, are what is a polynomial component. Usually, it is one of these two orders, so the first order polynomial, which is a local level model, which can be represented like this, and then we can identify the observation matrix and the state evolution matrix at just one, or the linear growth model that has the following matrices F and G, and in a more general form, the nth order polynomial model will look like this with G matrix n by n, and it will be all zeros minus the diagonal and the diagonal row above it. Okay, and another, it is also common well, it's very common to assess some type of seasonality in time series applications. For example, if we are trying to forecast sales of ice cream, the demand is usually higher during the summer. If we are looking at forecasting a time series about I don't know, passengers in the subway or metro at peak commuting hours, the number of passengers is much higher than during other hours. So it's we would expect that the presence of a seasonality of period 24 if we are looking at a hourly time series. And the way to account for these possible seasonalities is through a seasonality building block. And for a period S seasonality, the corresponding observation matrix and state evolution matrix look like this. With dimensions s minus 1 by s minus 1 and just s minus 1 in case of a univariate model. And it's possible to have the different seasonalities combined into the same model. That's just different building blocks. And taking the previous example about ice creams, for examples, it makes sense to use some covariate like the temperature because it's probably related to the demand for ice creams. And it's straightforward to include some covariate USAPT into a DLM. And for that, the evolution matrix or vector is just the transpose of of those covariates. And the transition matrix is just the identity of corresponding dimension. And also take into account that when forecasting future values, UT plus the whatever horizon we are interested in, the value of this covariates must be known or have its own forecast, for example, with another model. Or we could also just assume that it stays the same. Okay, so for example, with just three building blocks or model components and a linear growth in violet, a seasonal period, a seasonality of period 4, and a covariate of just one variable. The evolution matrix and observation matrix will look like this, where this one is the linear growth, the seasonality of period 4, and the component for the covariate. And well, the update and forecast procedure for this type of models is done through the Kalman filter. And if we denote the available information at the beginning of the period t as this sub t, and that is the previous information as the previous observation, plus also if there were any covariates, they will also be included here. If we have this, the sequential update procedure is like this. The one step ahead pretty distribution for the states given the information available at the beginning of that period before the observation is given by a normal distribution with this mean and variance. And the one step ahead pretty distribution for the observations is also a normal with this mean and this variance. And the filtering or posterior distribution after we have observed the YT, it's also a normal distribution. So this makes the update and forecast procedure quite fast, and as we can save, for example, the current state in a database, is the online, using this for online forecasting is quite advantageous compared to other type of models. And a common problem experience when trying to apply this type of models to different use cases is the difficulty in specifying the variance matrices for the observation and transition model. And an option is to use just maximum likelihood, but another more common and recommended option is to use what are called discount factors. When using this, we for the variance of the observation, we just use the identity matrix of corresponding dimension, and for the state transition matrix, we use what are called the discount factors delta, which take values between 0 and 1 and specify the increase in uncertainty between one time period and the next one. It changes the variance of the predicted distribution for the states. And previously, if we use the the classical method of using WT, the variance of the predicted distribution for the state will be this part plus WT, as we saw in the previous slide. But if we use the recommended method of discount factors, it will be divided by the corresponding discount factors. And if we have bigger uncertainty, this value will be lower. And if we have less uncertainty about future values, it will be higher. In practice, these discount factors take values which are relatively high, between 0.8 and 0.99. And it is possible to use different discount factors for different components in the model. And also sometimes it's also interesting to use what we call adaptive discount factors, and you can monitor the performance of the model. And if there are a lot of observations that end up outside the credible intervals, for example, if you are computing the 95% credible intervals and you have a number much bigger than the 5% of observations that end up outside those intervals, you can reduce the discount factor to try to better adapt to that new situation during some horizon, and then going back to the previous discount factor. Okay, an extension of this type of models is what is called dynamic generalized linear models, which extend the observations to any distribution of the exponential family. That is a distribution that can be expressed in the following manner. For some defining quantities, eta t, bt, and functions t, a, and b. The dynamic generalized model for the series is defined also by an observation model and a state transition model and prior information for the initial state. In this case, we have a link function g, which maps the natural parameter eta t of the exponential distribution to the real line. And note that here we are not assuming a normal distribution or any distribution for WT, but and the states, but just the first moments, the mean and the variance. And well, similar to a DLM, the updating and forecast procedure is done in a sequential manner, but in this case we have to use a moment machine for computing it. And also at a time t, given the available information at the beginning of that time period, we can compute one step ahead prior moments, which in this case are just the same. And in case of using the discount factor, this will be divided by the discount factor. And for the one step ahead predicted distribution of the observations, we can calculate the conjugacy-induced pretty distribution for the exponential family that we are using, uh, for distribution of the exponential family that we are using, and with the hyperparameters calculated using moment matching. And the posterior moments for the state after observing the y sub t are also calculated in a similar manner, and we also use moment matching for calculating the hyperparameters. And I'm going to present now some applications of this type of structural time series models. The first one was about forecasting aviation incidents or occurrences, which are safety occurrences that can be without any severity or can be very severe and incurring fatalities, injured people, and loss of material, etc. This was part of a project for the Spanish Aviation Safety Agency, and it was a project for aviation safety risk management support, and it was for the National Aviation Safety Plan. And there were 86 types of safety occurrences, uh, which some of them were bird strikes, runaway incidents, um communication incidents, etc. And all these occurrences or incidents were classified according to the five severity levels provided by the International Civil Aviation Organization. And they, as I said, could entail the most severe ones, could entail fatalities and injuries for people. And we had also that data about the number of these fatalities, injuries, and the severity of them. Okay, the data was monthly data, and although we were also interested in some aggregated forecasts, etc., but mainly we were focused on the monthly granularity. And for each airport, we had data about the number of occurrences of those 86 type of occurrences, the number of operations. This is a number of flights. And exploring these occurrences, we saw several effects in some of them. Some presented what we call a stress effect. This stress effect means that higher number of operations inducing higher occurrences rates per operation. And this could be, for example, expected this could be caused, for example, by I don't know, material fatigue or fatigue of the personnel, etc. It's also common to observe some trend effect, seasonality effects, for example, with bird strikes if they are caused by migratory species. And here we have a table of the different types of effects detected in, well, the number of occurrences that presented the different effects. Some didn't present any effect, others presented several effects at the same time, etc. For the most simple type of occurrences, a simple model like this conjugate gamma Poisson model can be used with more or less success, and it's extremely simple to obtain posterior probabilities and predictive distributions with this type of model, just using the conjugate distributions. We also provided some variants of this model that require to use Markov chain Monte Carlo to sample from the posteriors. But For the most complex ones, we propose this type of model, which combines the Poisson part for the observations x sub k and the logarithm of the occurrence rate per operation is modeled through a standard DLM. So we have the influence diagram here at the bottom, in which the Poisson part is in red and the DLM part in blue. And since this is not a standard distribution, the observation model is not a normal distribution, we couldn't use the standard Kalman filter, so we propose the use of a particle filter. And it consisted in, for each time step k, generating capital N different particles, evolving them, and with the equations, and then we obtain an approximation of the predicted distribution for that period. And then the equivalent of the second step is just the update with the new observation. For that, we also evolve the states and compute the likelihood with that with the likelihood of that new observations, update the current weights with the likelihood of the new observations, normalize the weights so they add up to one, and at the end of each of these steps, we compute the effective sample size, and if it drops below a certain threshold alpha, which usually is just half of the observations, capital N divided by 2. If it drops below that level, we resample. And the last step is just the propagation of the states to the next period. And it's also possible to use Markov chain Monte Carlo for this type of models, but um, the main problem of doing that is that for some applications, well, the main problem when using Markov chain Monte Carlo for this state space models is that with each new observation you have to restart the chain, and in some applications that require online forecasting, this is a disadvantage. Okay, and looking at a specific at a specific occurrence, once here, which once here is when there is a sudden change in wind direction or intensity. This is a problem, especially at low altitude. At high altitude, this can be just feel as a turbulence, but low altitude, when a plane is taking off or landing, and this is quite dangerous. Can be quite dangerous if it is a severe occurrence. Okay, and looking at the data of this type of occurrence, we saw that there was not appreciable stress effect, which is comprehensible. There was a seasonal effect, which also makes sense in most locations. It could be a linear trend and also a group effect with two groups, one of more coast for airports located in coastal areas and one for more interior airports. And for this, we propose a hierarchical model of the previous Poisson DLM model, in which Y denotes each of the two groups, and we have the same prior distribution for both of them. And F and G have as components, as building blocks, a linear growth and a period 12 seasonal component to take into account that those effects that we saw on the previous slide. And the variances for the observations and the state evolution are estimated using maximum likelihood. And for the initial state, the variance is just the identity, and the mean is initialized with the first year of data. Uh, Here I present an example of the use of this model with this occurrence. And as we can see, it seems to adequately forecast the observations, and we provide the point forecast, which is the solid line, and the 95% credible intervals, and, which is the dashed line. And well, it's to be expected that about 5% of the observations fall outside of those credible intervals. And as we see here, comparing this model with the standard DLM and other models for non-negative observation, integer value observations, we can see that according to the most common metrics like mean square error, mean absolute error, our model performs better than those. And also we can see here in this coverage plot that the credible intervals seem to be quite good and better than the alternatives. And for example, the most interesting ones and most compute ones, which are the 90, 95, 99% credible intervals, they are quite close to the ideal coverage of the 90, 95, 99% coverage of the cases. Okay, and another use case that I encountered during my industrial PhD thesis was the problem of supermarket demand forecasting. In this case, we had many different time series, some of them corresponding to high demand products, so they didn't present almost any any observation with a value of 0. And we also had some products with very low demand. So when we look at them at the granularity level that we wanted, which was daily time series forecasting, when we looked at the level, this type of products presented many zeros, which can be a problem with some type of models. And well, this was a project for a large retail company, which had thousands of stores around different countries. And each store had itself thousands of references. And this forecasting problem was quite important because there was in this store there is not uh, there is not a lot of space to beyond the shelf to stock the product, so you have to be quite accurate with the forecasting, because you don't have a lot of flexibility in the stock you can have in that store. And when looking at the different effects, we also saw that there was different trends. For example, with new items, usually it started low, but it quickly it quickly went up in demand. There was seasonality, for example, with ice cream, as I said earlier. And there was a lot of cases with overdispersion, and that is where the variance is much higher than the variance of the model. If we are supposing a Poisson, it's quite usual to observe this in low demand products because the variance is usually higher than the mean. There was also influence about the price, promotions, substitute goods, etc. And for dealing with these problems, especially with the problem of the presence of a lot of zero observation, which is common, as I said, in low demand products, uh, is usually one of two approaches is used. One is a zero inflated model, which puts extra probability to the zero occurrences, and another one is the use of what is called a hurdle shifted model, which is a mixture of two models, and it has the advantage that the probability of zero occurrences can be inflated as well as deflated. And we chose this second approach and propose a DGLM mixture for dealing with this type of problems or with this type of time series. And here we define the original time series and a binary time series of sale, no sale. Is 0 when there are no sales and 1 if the sales are 1 or bigger. And this mixture has two DGLMs. For the binary time series, a Bernoulli DGLM, and for the shifted number of observations, we have a negative binomial DGLM. So we have we assume observation from a negative binomial for one and from a Bernoulli for the other. And as link functions, we use logit and the logarithm. And we assume the parameter r of the negative binomial stays constant because otherwise this will not be could not be expressed as a member of the exponential family distribution. And the reason for using a negative binomial instead of a Poisson is because it is more flexible for situations where there is overdispersion. Okay, so the fitting and forecast procedure for this type of proposed models is done as I presented in the previous slide for a general DGLM, and the result is the following. For the one step ahead forecast for the states is like always. The one step ahead forecast for the distributions is a Bernoulli for the binary time series and a beta negative binomial for the time series for the shifted time series of the observations. And the updated and forecasting or the update of the states after observing the YT is also done in the same manner using moment matching, and the resulting forecasting distribution is a mixture of a beta and a beta negative binomial. And an advantage of this type of models is that the forecasts are not just a point forecast, but a full distribution, which has some useful applications. One is that we can compute the probability of out of stock events. That is when we run out of stock. We run out of stock. We do not have a stock in a store for some product because we have sell all available stock. And well, so if we define the available stock at the end of some time period t as the stock on the previous time period minus the sales in that period plus the resupply that arrives in that period, we can compute the probability, and using the forecasting distribution, we can compute the probability that the demand is bigger than the available stock in that period, and we can compute the probability of an out of stock event for some horizon. For example, here we have for some type of beer, we have the probability of an out of stock event of running out of stock for a whole week. For example, for the 3 first days, the probability of running out of stocks is very low, below 20%. And once we go above the fourth day, the probability of running out of stock starts to be really high. So using this probability of out of stock, we can use several criteria to make informed decisions on when and what in what quantity to place an restock order. The most simple criteria will just be to use a threshold alpha. For example, here a threshold of 0.6, then we will place an order when the fourth day, because the next day the probability of an out of stock event is more than we are comfortable assuming. If we have more information like storage cost and the price of the product, etc., we can compute the expected profit of reordering or not doing anything or not reordering, and we can place an order when the expected profit is of not doing the order is worse than doing the order. And also, we could even consider some utility function which takes into account the risk aversion of the company. Okay. Here we have a couple of examples of time series, with the observations being the black points, and the forecast, the point forecast, the continuous line, and the dash line, the credible intervals for two different type series. The one above, the one for the beer, is a product of the like the ones we call a high demand product, and the one below that we see that has a lot of zero observations is what we call a low demand product. In this case, the Bernoulli part of the mixture has a higher relevance than the negative binomial part. Okay, and we also presented a variant of the univariate model, but using multivariate distributions to better take advantage of in cross-series information. And it is quite similar to the univariate models, but in this case, we have a vector YT of several products M, and and we also have a binary time series of 0 or 0 observations. And we also have two parts. We have a mixture, but in this case of two multivariate DGLMs, we have a multivariate Bernoulli and a multivariate negative binomial. And as link functions, we have generalizations of the logit and the logarithm. And here we can see that an examples of a family of beers that benefited that provided that in which the use of these multivariate models provided better forecast than the use of univariate models. And this is for here we have represented the forecast for two types of beers of this family, and the credible intervals, which are really close to the ideal coverage represented by the dash line. And this was all done as part of my industrial PhD, which was between this institute and another consulting company. And so for implementing all these models and solving all these problems of the projects with the other companies, I had to develop a Python package which was developed using an object-oriented programming paradigm, at least for the classes of the DLMs and DGLMs, and some more functional paradigm for the other for the tools and specific models. And well, this model had all the necessary parts to applying standard DLMs and DGLMs to time series. Also, some functions and tools for aiding in exploratory analysis and time series monitoring, for monitoring the performance of the models in those time series. It also provided some functions for computing and using the probability of out of stock occurrences for saving the model, the states of the models into a database and then recovering them for doing sequential updating with just the last observation. The models for the proposed for the aviation problem were included also, and the models for this supermarket sales forecasting and also some other similar variants. And well, as this was developed for the company, it's not available in PyPy or other repository, but there are some other alternatives if any of you want to do something similar or has some similar problem of time series forecasting. For R, a package that is quite good is called ELM. And for Python, there are a couple. One of them is PyDLM. The other one is PyBats. DLM and PyDLM only have available DLMs. So we only have normal distributions for the observations and the states. And PyBats does include the GLMs. If you want a recommendation, I think I would recommend the use of PyBats, which is Python Bayesian analysis of time series, I think the name. And it's the one I would recommend from these three, also because it's in Python. And well, some conclusions of this session are that, well, state space model provide a flexible framework for either inferring the hidden states or predicting future observations. There are multiple possibilities to infer the hidden state, like the EM algorithm that we saw earlier, or stock gradient descent, the spectral methods, blocked Gibbs, depending on the application. We could be interested in one or the other. Linear dynamic system or DLMs allow modular construction of interpretable components for the seasonality, trend, covariance, etc., via the block diagonal behavior. And the extension, well, DGLMs extend the DLMs to non-Gaussian observations, which are useful in many cases, like for the count time series on the supermarket forecast problem. And the application to vision incidents and supermarket demand, so that these type of models are competitive with other state-of-the-art models, and they offer some more richer probabilistic outputs that can be used to take better decisions than for distribution and other practical problems. Okay, so thank you for everything. And are there any questions about the session?
Hi, I do have a
Hi.
question.
Yeah.
Well, two of them. The first one is not actually a question, it's more that I didn't really understand in the generalized dynamic linear models.
Uh-huh.
You introduce a G function. I didn't really understand it. I don't know if, well, maybe you can relate it with the examples.
Okay. So 1 second. Okay. This G
Yeah, that
function.
one.
Yeah, this depends on the type of distribution of the exponential family you're using. If it is the normal distribution, the G function is the just the identity. This is G eta t. I think is eta t. It depends on the
Ah, okay, so it depends on the model.
it depends on the type of the of distribution of the exponential family you're using,
Okay,
and it's just to sorry, it's just to map this eta t from the this natural parameter from whatever it is here to the real line.
okay, okay. Thank you. And then also, well, in one of the samples,
Uh-huh.
you have like the prediction of the time series,
Yeah,
but also you have like the prediction several steps there in that picture. You have
yeah,
the prediction several step ahead,
yeah,
like instead of using the one step ahead typical of the Kalman filter,
yeah,
you
yeah.
predict steps. Do you know if the covariance matrix does it converge to a certain value or it diverges in some sense? It tends to infinity.
It
Covariance.
tends to increase when you are when you increase the horizon of the forecast. It
Yeah.
just starts to it continues to increase.
Okay. And yeah, that was all. Thank you for the talk.
Okay.
I do have some questions, Bruno. One of them in this DLM literature,
Uh-huh.
we have, as you said, we have to decide for building blocks, no?
Hmm.
Depending
Yeah.
on seasonalities or linear trends. But that's somehow of a design choice, right? Like
Yeah.
how do you choose whether you're interested in a specific seasonality of period or frequency, whatever, or why do you how do you choose if you want an nth polynomial trend? Is
Hmm.
it something that you
Yeah.
first visualize the data and then
Mhm.
try to find a good fit, or
Mhm. Yeah, yeah, the process is more or less what you said. First, you do some exploratory analysis. For example, you compute the autocorrelation function and try to see if there are some seasonality. In this case, for example, it's quite clear that there is a period 12 seasonality, and this can be automated. And in fact, we did some work to try to automate it in a project that we did for a pharma here at ISMAT. And also with the trend, you explore the time series and try to determine, well, and try to determine some possible values, and then you can apply the different models and decide according to some metric and looking at the performance of the forecast, you can decide on a final model. Usually, the polynomial part, it's usually only the local level model, that's the first order polynomial or the linear trend model, are used, because the other ones are really well are quite unstable, and above the third order polynomial, which is the cubic trend, they are not used.
okay. And in that example that you're putting, why is it that the number of wind shear occurrences increases in time? Well, I guess it's something specific from the data, but do you have any idea?
I don't
Mm.
remember now, but yeah,
Uh,
yeah.
no, it just surprised me that.
The increases from this year to this one, and then it stays more or less stable,
Sure.
but I don't remember the cause for this.
Okay, fair. That's fine. Thank you.
Okay, so thank you,
Uh,
everyone.
yeah, I don't think we have any other questions. Um, so I guess we can finish the session here. Thank you so much. Yeah. Next session is going to be by Jose Manuel Camacho on decisions,
Mhm.
May 13th, and we hope to see you there. Thank you so much, Bruno, for your time,
Thank you.
and see you next time.
Okay.